Hi, everybody. What I'd like to do today is continue on with the lava flow information that we started last week. We're going to finish up some of the background material on cooling, and then we'll move into looking at some real lava flows. So if you remember from last class, the emphasis there was to learn about the different types of cooling. And we talked about radiative cooling, convective cooling, and conductive cooling. Now, radiative cooling is heat loss essentially through light. It's not always light we can see. A lot of the heat loss is in the infrared range. But if you go back and look at the equations for radiative heat loss, it's extremely high when the surface temperature is really hot. In other words, when the stuff first erupts on the ground and it's glowing red, that's when radiative loss dominates. And because it is so dominant, it actually only is important for a few seconds. It gives off so much heat and the surface temperature plummets so rapidly that the other forms of heat loss become more dominant really quick. So when stuff is first erupted, all of that light coming off the lava flow quickly cools and starts to form a crust. And then once you have a crust, you have a thermal gradient. You have a cooled surface and you still have a much hotter interior. And then conduction tends to dominate. And remember, conduction is movement of heat through material that has a thermal gradient. So basically, if we boil down cooling of lava flows, radiation is really important when the stuff comes out and it's red hot, and then conduction dominates. We talked about convection. Convection is really important in some environments, um, underwater environments, and places where the atmosphere is really heavy and dense. Here on Earth, it's not so important. You do get some right away along with radiation, but for the most part, we end up ignoring it for subaerial lava flows. So that brings us to this diagram that I have here. And what it's doing is it is showing 3 time steps. So right here is when the lava first comes out. T1 is sometime a little later, and T2 is sometime a little later than that. You could also think of it as being related to the distance from the vent. Right near the vent, all the material comes out, it's all eruption temperature, it's all hot. So there's no variation in temperature from the top of the flow. And this is a side view, so that's the top of the flow. And then this is the base of the flow right there. And then underneath is some sort of rock or soil unit. And then this arrow right here indicates distance from the vent. So as it moves, it cools. Initially, you get lots of heat that comes off due to radiation. And then once you form a little crust, then it's mostly conduction. And what this diagram is showing is that the upper crust actually grows a lot quicker than the lower crust. And the reason the upper crust grows so quick is that, for one thing, it's allowed to radiate into the environment. It doesn't radiate into the ground. It just radiates into the air, into space, if you're in that kind of an environment. So the bottom crust just grows a lot more slowly. It has to conduct heat into the ground, and that's a much slower process. Okay, to summarize, we have 3 types of cooling. Convection is simply not important in subaerial environments. It's important in submarine environments, and it's important in some planetary environments. But on the Earth's continents, we tend to ignore it. So that leaves us with 2 dominant heat loss mechanisms. One is radiation, which only has to do with the surface temperature. So when the surface temperature is super hot, when it first comes out on the ground and it's bright red and glowing, then radiation is the dominant heat loss. And it's so dominant that the temperature of the surface plummets rapidly. And of course, as that surface plummets rapidly, that makes radiation less and less important. What happens is radiation quickly forms a crust on a lava flow. And once you have a crust, then conduction takes over. And conduction is the way that the lava flows lose the vast majority of their heat. Initially, you form a crust through radiation, and then conduction. Heat is just slowly moving out of the center of the flow to the edges of the flow. And in this case, you have a surface that's exposed to the atmosphere, and you have a base that's in contact with the ground. Conduction into the air is going to be much more effective than conduction into the ground because the ground is a poor conductor of heat. So in this case, what you're seeing is that the surface crust grows more quickly than your basal crust. And that's all that this diagram is really designed to show you. Radiation forms a crust because of the tremendous heat loss, because of the surface temperature is high. Once you have a crust, then conduction takes over. Conduction into the air is much more efficient than conduction into the ground, so it grows more quickly from the surface than it does from the base. Okay, so we're going to move on now and look at some different types of lava flows. Today we're going to talk about basaltic lava flows. Basaltic lava flows are arguably the most important kind of lava flow in the solar system. The vast majority of the Earth's surface, where volcanic, is from basalt. The moon is basalt. Lots of our um, terrestrial planetary surfaces, the surfaces of Mars and Mercury and Venus, are dominated by basaltic volcanism. And even some of our outer satellites have some nice basaltic surfaces as well. And there's a lot of different ways of looking at basaltic lava flows. One of the most simple and thought-provoking ways I've seen of looking at basaltic lava flows was put out by a researcher named Chris Kilburn. And he basically breaks basaltic lava flows into two types. He calls them core-dominated and crust-dominated. Core-dominated lava flows are where the hot core of the lava flow controls all of the movement. It does form a crust, but the hot core moves forward and breaks up that crust into smaller and smaller pieces. It kind of moves as a mass with as one big flow mass. A crust form, it gets broken up as the flow continues to move downhill. This is how we get lava flows and block flows. And if you watch the video that's listed here, you will see the lava flows move as a giant mass and that the surface just gets continually broken up into smaller and smaller, cool, clinkery pieces. And a lot of these clinkery pieces sort of fall off the flow front, and then the flow just sort of mows them over. And so you get a base of clinker and you get a top of clinker, and the main body of the flow is just one giant mass that then cools off. So these are called core dominated lava flows. And again, it's the hot, massive core of the lava flow that controls all of the movement. These things tend to move at a brisk walking speed. If you watch the video, you will get a sense of the movement itself. The second type of lava flow, when we have basalt present, is called a crust-dominated lava flow. And this is where the cooled crust significantly retards and shapes the flow. Pahoehoe lava flows fall into this. You'll see them form a crust, and then you won't see anything really happen for a second, and then lava will break out through the cooled crust and form nice little Pahoehoe toes. It's a really interesting process to watch. I've listed a video here that show you how Pahoehoe flows grow. And one interesting thing about Pahoehoe flows is that not only do they form these really cool Pahoehoe toes and ropes and various flow features, but the entire mass of the flow tends to inflate over time. And if you watch these videos and you sort of watch the back part of the flows that had been in place several minutes earlier, you will see the whole area start to rise up and inflate. And sometimes inflation can be fairly significant, raising the surface of the lava flow 10 meters or more. So these are interesting ways for lava flows to form. They're really fun to watch, actually. But you can see in these two videos, the core dominated, where the crust really doesn't provide any significant um, stoppage of the flow just keeps moving along because the core is moving so fast. And then a crust dominated flow where the crust um, retards the flow in a significant way, forming lots of these little breakouts and pahoehoe toes and so on. So watch these two videos and you'll see the difference between a core dominated flow and a crust dominated flow. So pahoehoe flows are crust dominated. These form a crust which holds back the flow. Eventually, though, the flow will break through the crusted flow surface and you'll get little tongues and breakouts and flow lobes. And because it forms a crust and because the cooling then has to occur through conduction, that takes a long time. And these interiors remain fluid for quite some time. Most lava flows take months to years to flow. There's been some lava lakes that have taken decades. In fact, there's a lava lake at Kilauea volcano called Kilauea Iki. It was hundreds of feet deep. It formed in 1959, and it's still hot today. If you go there, you can see fumaroles still venting gases. So again, slow cooling through conduction keeps a nice hot interior for many, many years and decades. Sometimes on the surfaces of these crust-dominated pahoehoe flows, you can build up pressure in the interior and form these lava blisters called tumuli that are fairly prominent on the surfaces of lots of Hawaiian lava flows. Sometimes they're a couple of meters tall, like this one. Sometimes they can be 10 meters or so tall, and they simply represent places where the flow interior builds up some pressure. Sometimes that can happen at bends in interior flow pathways in the flow. Think of the flow being crusted over and then hot material moving underneath. Sometimes that material doesn't flow in a nice consistent pattern. You get little sub pathways that start to develop. Some areas are a little hotter than others, so the flow is preferred there. And whenever you get a bend in that um, sort of flow path, you can get these tumuli that form on top. And basically, they're just lava blisters. There's some, this is at Craters of the Moon, I believe, in Idaho, and you can see some lava blisters in the background just sticking up above the ground surface. The neat thing about pahoehoe flows, which again are crust dominated, is that the crust gets contorted because of the lava beneath still trying to move forward. So you get these really cool folds and ropes. Here's a different view of some of these ropes. You can see that the material must have had some strength, but it wasn't totally brittle when it formed. So it's an interesting feature that forms when you do have a flow crust, but the flow crust still behaves in a plastic manner and not brittly. Core dominated flows, you don't get the nice flow surfaces because the interior is moving so rapidly and breaking the crust up so thick, so quickly that you don't get massive sections of crust that can then be deformed plastically. So what you end up with is sort of a rubbly, blocky, scoriaceous crust that gets pushed off and broken, and then the lava flow itself just sort of rolls over the top of it. That process of breaking up a lava flow's own crust by movement is something that we call autobrecciation. And this tends to happen in lavas that have a much higher yield strength. So it's lavas that have um, either crystallized a little bit or lost a little bit of gas. They're starting to get more viscous and they're starting to develop really strong yield strength. So that's what a lava flow looks like. It moves at a brisk walking pace. You can see that the surface is a mixture of blocky, cooled areas and then newer, hotter areas. Those hot areas are going to lose their heat radiatively and quickly crust over. But as the flow moves forward, that crust just gets broken apart. Stuff sloughs off the flow front and the flow runs it over. And that process, again, of breaking up one's own crust is called autobrecciation. Another view of core-dominated flow on top, flowing over a crust-dominated Pahoehoe flow. This is at Kilauea volcano in Hawaii as well. Now, what's interesting about these two very different looking lavas is that they're made of exactly the same material. This material here, the is exactly the same as this material here, Pahoehoe. Chemically, it's similar in every way. It's the exact same stuff. So the question has always been, well, why do sometimes we get basalt come out and it looks very ropey, and other times it comes out and it looks very clinkery and blocky? Well, a couple of researchers, um, Peterson and Tilling from the USGS, studied this back in the 1950s and 60s, and they watched lava flows come out of Hawaii, and they noted several things with respect to Pahoehoe and Aa. First thing they notice is that all basalts initially erupt as Pahoehoe. When they first come out on the ground, they are smooth and ropey and tend to be crust dominated. But some Pahoehoe can turn into Aa, and they noticed that happened when two things occurred. Either there was an increase in strain rate, in other words, the flow started moving faster. That typically occurs when the flow moves over steep slopes. So what they commonly saw is that if lava was flowing over a really gradual slope, it would be Pahoehoe. And the minute it would go over something really steep, like a small cliff, it would turn into Aa. They also noted that sometimes lava could be going down a fairly consistent slope, and the longer it flowed and the farther it got away from the vent, the more apt it was to transition from Pahoehoe to Aa. So their interpretation was that the lava was cooling off, crystals were forming, bubbles were forming, maybe it was losing a little gas, and its viscosity was getting greater. And the yield strength was probably getting greater as well. Basically, it was becoming a thicker, more pasty version of itself. And when that occurred, it changed into Aa as well. They also noticed, and I always found this very interesting, that Pahoehoe can turn into Aa, but they never saw it go the other way. They never saw an Aa flow turn into a Pahoehoe flow. So with these observations in mind, they came up with a little diagram that sort of showed how they thought the transition from Pahoehoe to Aa worked. So in this field in the upper right, up in here, we have Aa. And down here in the lower left, we have Pahoehoe. And this is a plot of viscosity on the bottom. So we have low viscosity over on the left, really fluid and runny. Higher viscosity over on the right, much more thick and pasty. And then on the y-axis, we have rate of shear. You can think of it as speed of flow. So you could also think of it as slope. So over here we have low slope or low speed, and up top here we have high speed or high slope. So when you have slow moving, really fluid magma come out on the surface of the earth, you tend to form Pahoehoe. So you'll be down in this region here. Really fluid, really low slope, moving very slowly. That prefers a surface crust. So these tend to be crust dominated flows. But when you have high rates of shear, high slopes, fast moving, then the crust isn't as much of an impediment to the flow moving. The flow has much momentum from the increase in slope, and you tend to get Aa lavas. You also tend to get Aa lavas when the viscosity is high. So when you have high viscosity and high shear, you tend to get blocky or Aa flows. Where you have low flow rates and you have very high fluidity, you tend to get Pahoehoe. So when you move over a steep slope and the rate of shear increases, you're more likely to move into your ah. Or if your flow's been out on the surface for a while and it's forming crystals and bubbles and it's getting more viscous, your Pahoehoe flow can turn into an ah flow as well. So the transition from Pahoehoe to ah is dominated either by a change in the rate of shear, basically speeding up the lava flow, probably from going over a steep slope, or it can be due to a viscosity increase as bubbles and crystals form in your flowing lava and as it's cooling off. So that tends to explain all of the different observations that Peterson and Tilling made about Pahoehoe and Aa flows. Here you can see where lava is flowing over a steep slope. Sometimes it can be fluid enough to remain Pahoehoe, but sometimes it might be a little more viscous and thick, and you can form these little Aa stringers that you get here. So this is a photo I took in Hawaii a few years ago, and it basically shows both types of lava. The chemistry is exactly the same between these two lava flows, just slightly different changes in viscosity, in this case, most likely explaining the differences in morphology between the Pahoehoe and the Aa. Okay, so one of the more interesting types of basaltic eruptions are flood basalts. I could teach a whole class on flood basalts, but I'm just going to give you a couple of slides here. These are massive basalt flows that are found in various places on Earth and various ages. We have flood basalts that date back to the Archean that you can find in the Canadian Shield. And we can find more recent ones, just tens of millions of years old, that have formed in the Columbia River area or in the Deccan area of India. Um, these appear to be massive eruptions that flow great distances. They can cover hundreds of square kilometers. They have great thicknesses, a kilometer or more. And they appear to be eruptions that happen over pretty short geologic timescales, a couple million years. The Columbia River basalts up in Washington appeared to have flowed over a pretty flat slope. The average slope in that area is just a degree or two, but somehow these lava flows managed to make it 300 miles from eastern Washington, right on the border with Idaho. These flood basalts made it all the way to where the Pacific Ocean is today. They're fairly rare in the geologic record, but over the last 4.6 billion years, there's been dozens of these things. And they tend to happen in areas that are undergoing extension. So in eastern Washington, we have an extensional area, and you tend to get rift zones or cracks in the Earth's surface that allow magma to pour out in great quantities. Here you can see some um, stacks of lava flows. I believe these are from India. The interesting thing about flood basalts is they were first really recognized by geologists back in the 1950s. And because they traveled so far, it was assumed that these lavas had to come out on the ground really quickly and travel really fast so that they could move hundreds of kilometers without freezing solid and becoming rock. And geologists just sort of went with that idea for a long time. But it was a few volcanologists in the 1990s that noticed something interesting, and it was something we just talked about, the Pahoehoe Aa thing. Now you remember, if lavas move fast, if they have a strain rate that's really high, they should be Aa lavas. But if you look at flood basalts, which are supposed to be really rapid moving, every single flood basalt on planet Earth is all Pahoehoe. That doesn't seem to fit with this idea that these were floods. And now some researchers are suggesting that these lava flows aren't actually fast moving floods, but they're super slow moving flows similar to what we have in Hawaii, where you get a crust and the crust insulates the flow. and then the flow can travel great distances beneath this cooled insulating crust, perhaps through lava tubes and other subsurface structures. Um, However, I did some research a few years ago and published that it was essentially impossible to move lava through a tube hundreds of kilometers without a huge pressure source. And in fact, there has to be so much pressure to drive lava that great of a distance that it would basically just blow the lava tube and the lava flow apart. What it comes down to is my research showed that you cannot create enough pressure to drive lava hundreds of miles through lava tubes without blowing the lava flow apart itself. And the other thing that's really interesting is that these geologists are suggesting that lava is flowing beneath the cooled crust through a series of tubes and pathways, but there has never been any lava tubes found in flood basalts. So we're at kind of a conundrum here in the volcanological world where there's evidence that these eruptions cannot be quick because we don't see um, but the math shows that they can't be slow either. So there's currently a lot of debate on the topic. I've kind of fallen into the um, idea that these things move slow so fast that they never form a crust. They constantly are moving and they're very turbulent in their movement, and that a crust can't form and be stable quick enough to form Um, and there's several volcanologists that agree with me and several that don't. So we're again sort of left right now with an unsatisfactory explanation for how flood basalts form.